Okay, let's get going. So someone just wanted clarification just in this previous problem. There were 2 steel beams here and each beam weighed 60 kilograms per metre. Okay, if we just go back to the bigger picture. So there were 2 beams here and you were looking at the weight on one beam. Because you only need to design one beam because they're identical. So you'd work all the loading out on one beam. Okay. So, example 2. We have a timber plank, 200 mil thick here, 6 metres long, the timber plank itself, but it's been supported, it's supporting a live load here of 5. So the live load here is 5 kPa, kilonewtons per metre squared. The plank is then supported by 2 equally loaded steel beams, each 10 metres long. And they tell us the weight of the steel beam. So this steel beam here, each of them weigh 100 kilograms per metre. Calculate the dead load and the live load on each steel beam in kilonewtons per metre squared. So this time round, if I drew my steel beam, 10 metres long, I can't say, well, it's got one load over the entire steel beam. That would be wrong. Because as you can see, one side of the beam is more heavily loaded than the other side. So when you come to do this problem, you have to say to yourself, okay, I have one load that runs the entire length of the steel beam, and that is the weight of the steel itself, which is my 100 kilograms per metre. Then on that steel beam, over the 6 metres, this is then where I have the weight of the deck, and then the weight of the live load. So when we draw it up this time, we actually have to draw a picture of it to show where the load is acting. So we're asked to calculate the dead and the live load. So when I come and do the dead load, my dead load I will have a dead load 1 and a dead load 2 component, and the dead load 2 is just the steel weight. Then when I come and work out the live load, I just have a live load acting on the left-hand side 6 metres of the beam. Does that make sense? Okay, what people tend to do is they take the average of it and they spread it evenly. That's not what is there in reality. You have to model what is there in reality. Okay, let's do some numbers. Calculate the dead and live load, part A on each steel beam. So it's telling us again on one beam. And it says on each steel beam. Once again, that includes the weight of the steel beam in kilonewtons per metres. And then calculate the ultimate design load in kilonewton per metre on each steel beam. And they were kind to you that year. This is a very old exam question. And because it tells you what the appropriate load factors are. I'm not sure we always tell you what the appropriate load factors are. We expect you to memorise 1.2 plus 1.5. It's not that hard. Then draw a diagram showing how the design load is acting on the beam. So they're telling you to draw it. Is everyone clear what the problem is? Yeah? Okay. So I think next week when this screen is working here, we'll be able to freeze that big picture. I was looking forward to freezing it today. Simple pleasures in life. Okay, so we have our G, which is our dead load, and that comprises the steel and the timber. So, our steel weight, well, that is our 100 kilograms per metre, and we know we multiply by 10 to convert it to kilonewtons, and we divide by 1,000 to convert to newtons and divide by 1,000. So we get our final answer in kilonewton per metre. Now, someone asked me about units earlier. They were doing a question in the book, working hard, which is what I like. There is a document on the Moodle site somewhere. I'm not sure where, if it's under resources or lecture material. It's called simply units.doc. Unit? I think it's called units.doc. It's, I think, a 3 or a 4 page document, and it just runs through unit conversion and things like that. So it might be worthwhile, if you're a bit rusty with your units, just downloading it and having a look at it and deciding if it's worthwhile printing it off. Okay? So we know the weight of our steel. Now, how about I give you a minute and you work out the weight of the deck in kilonewtons per metre on one steel beam equals, and what I'll do is I'll go back to the big slide so you can see the dimensions. So can you tell me what the load is in kilonewtons per metre, the weight of the deck? Sorry? Oh, you've worked it out already. 0.3? No? On one side? Someone over here said 4.5. 4.5? Okay, so what we do is, I'll do it both ways again. If I was dealing with just density times cross-sectional area, the cross-sectional area on one beam is this area in here. Yeah? And that area in there is 1.5 metres times the thickness of the deck is 0.2 metres thick. So that's my area, and I multiply that by the density of the timber, which we're told is 15, and that gives me a value of 4.5 kilonewtons per metre. So that's the quick way there. What I'll now do on the next overhead is I'll come in here and I'll do it the slightly longer way. I have the density. I'm going to multiply it by the total volume of the deck. 6 by 3 by 0.2. That's the volume. So by doing that, I now have a load in kilonewtons. So I want it on one beam only, and that's the load on 2 beams. So I'm going to divide by this. I'm writing beams in there so you can see it's 2, not 2 metres. So I divide it by 2 beams because I'm after the load on one steel beam. And then I want it per metre length. Now this is where people tend to then go, well, the length is 10 metres. No, it's the length over which the load acts. So that's our 6 metres. So when you do that, you get your 4.5, kilonewton per metre. So if I now draw the dead load here, I will draw a dead load on this side equal to 4.5 plus 1, which is 5.5 kilonewtons per metre. This is the dead load. And then on this side, where we only have the steel beam, that weight is 1 kilonewton per metre. So there's our dead load diagram. Let me just check if I have another. Okay, I can spread out. Now our live load, Q. So the live load we had acting was, remind myself, 5 kilonewtons per metre squared. So I'll do it the long way. We want to know what the live load is in kilonewtons per metre on one beam. So that's equal to our 5 kilonewtons per metre squared the total area over which that loading acts is our 3 by 6 metres. Now that gives me the total load on the whole system. So I'm going to divide by 2 beams. That unit now currently is still in kilonewtons. I want it in kilonewtons per metre, and the length over which it acts is 6 metres. So that gives me a live load of 7.5 kilonewtons per metre. Now, alternatively, what did we say? The live load in kilonewton per metre is just our 5. It's just our 5 kPa multiplied the width over which it acts. So what is the width over which it acts on one beam? 1.5 metres times 1.5 metres, which gives us 7.5 kilonewtons per metre. Do it whichever way you want. And that live load diagram now, that force is acting only on the 6 metre part of the beam. So the rest of the beam just only has steelwork there, so there's no live load acting. So just now, finally, part B was asking us for the ultimate limit state load, which is our 1.2 dead load plus 1.5 live load. So people see those numbers and they just want to stick everything in those numbers. You can't deal with this without the diagram now. So on this diagram, I have 5.5 kilonewton per metre dead load on that side. I have 1 kilonewton per metre dead load on that side. And I should put my dimensions in there, 6 metres and 4 metres. And then on this side, I have my live load here of 7.5 kilonewtons per metre live load. So that's my final ultimate limit state loading. Here is just 1.2 times 1, because all I have is dead load, kilonewton per metre. And over on this side here, it would be 1.2 times our total live load of 5.5 plus 1.5 times our, dead load of 5.5 plus 1.5 times our live load of 7.5, which is a load of 17.85 kilonewtons per metre. Now, just to clarify, when you go and do your strength calculations, you don't know how to do them yet. That's what I'll be teaching you. That's your starting point. So this here is your starting point for your ultimate, and I should unfreeze that now, shouldn't I? So this here is your starting point for your, I like changing colours, for your ultimate limit state design. But just be clear, you're designing that beam to carry that loading and it won't fall down with that loading, okay? But I go and stand on that deck and this thing is saggy baggy, okay? And I'm going to have this is going to be floating in the middle of a river and I'm going to have the band playing on this part of the beam and, you know, they're going to be very uncomfortable with it sagging everywhere. So it's important it doesn't move around too much. It's important it doesn't sag too much, or my band is going to be, won't want to go on it. So as well as doing a strength check, I have to limit how much that beam deflects. And the criteria is normally span on 200. So that beam is spanning 10 metres. So that is a span in millimetres of 10,000 millimetres, and I divide that by 200, 1, 2, 1, 2. So this thing cannot deflect more than 50 mil. If it deflects more than 50 mil, it's considered uncomfortable. It's considered unserviceable. So when I do that deflection calculation, I'm not going to put this big heavy load on there. The load I'm going to put on there is dead load plus 0.7 live load. So the dead load over here, the loading on the left-hand side, would just be my 1 kilonewtons per metre, and the load on my right-hand side would be 1 times 5.5 plus 0.7 times my 7.5, and I don't have a number here for that. Okay? But when you come and do your deflection calculations, you would base them on the lighter load. When you come and do your strength calculations, you would base it on the heavier load. Now say from that dead load calculation, the beam there isn't strong enough. When I do the deflection, it only deflects 40 mil. So in terms of deflection, it doesn't deflect too much, but in terms of strength, it's not strong enough. I have to put a bigger beam in. This time round, I do the strength calculation. The beam is well and truly strong enough. However, when I do my deflection check, it deflects 60 mil, 70 mil. So it's deflecting too much, I have to put a bigger beam in. So when you come and do the design process, you don't go, oh, it's only deflection, it doesn't matter, don't worry about it. You have to meet serviceability limit state requirements and ultimate limit state requirements. That's strength requirements and deflection requirements. You don't say, oh, who cares about deflection, it doesn't matter. It matters just as much as strength. But we've put smaller load factors on there. So when we do that deflection check, we're not actually doing it for as much load. Okay. I'm not going to do that one. That's the end. Next lecture, you will then get those loads. Shh, hang on, let me say one more thing. And we will learn how to calculate the reactions. That's the next step in our design process. We'll learn how to calculate reactions.